All right, everybody, welcome back. Today what we're going to do some polynomial long division. I'm actually going to show you the long division first, then I'm going to show you the box method after. Just, one of two ways in case one is easier than the other for you. For me at least, it is totally fine. It should help you get the right answer regardless. Okay, so we are going to divide 16x to the third minus 8x squared minus 27x plus 18 by 4x minus 3. So I'm going to set up my long division here. And now we're going to jump right in. All right, so how this is going to work is whenever we do division, we want to start to cancel the first part of what we are dividing by with the first part of what we are going to divide. All right, so in this case, I want to get 4x as close to 16x to the third as I can, just like we would with numerical long division. So we need to think about, what do I multiply 4x by to get it as close to 16x to the third as possible without going over? Well, luckily for us, I can multiply by a 4x squared. And I actually should write this here. The reason I wrote this over a little bit is so our x squareds are above each other, kind of just something I like to do to keep things organized. So just to show you what I'm doing on the side over here, I will do 4x squared times 4x minus 3. And if I multiply in, I get 16x to the third minus a 12x squared. So I'm going to put that right underneath the first two terms of the polynomial I am dividing. All right, and just like we do with regular long division, I am now going to subtract those values. So 16x to the third minus 16x to the third is 0. So that cancels out, and that's exactly what we want to do with our division process. Now I have negative 8x squared minus a negative 12x squared. Well, minus a negative always turns to a positive. So we have negative 8x squared plus 12x squared, which is going to give us a 4x squared. So I'm going to keep the division process going, and because I'm dividing by something that has two terms, I'm going to drop the next available term in my polynomial. So now I want my 4x to get as close as possible to 4x squared. Well, luckily that goes in pretty evenly as well. I can multiply by 4x, and I'll show you that work on the side here. We've got 4x times 4x minus 3. And I'm going to distribute in, and we get 16x squared minus 12x. So I actually don't need it to be a 4x. I just need to multiply by 1x. And here's my mistake. I think I was looking at the 4 at the bottom there. But if I just multiply by x, and I distribute in, we get 4x squared minus 3x. And then our first terms line up, so therefore when we do the subtraction, they're going to cancel. So I just need a regular x there. So I'm going to write this directly underneath once again. And remember, we are going to be subtracting the entire quantity. So I've got 4x squared minus 4x squared, which again cancels out, exactly what we want. And now I have negative 27x minus a negative 3x. Minus a negative turns to a positive, so it's negative 27x plus 3x, which is a negative 24x. And one more time, because we've got one more value to take care of, I'm going to drop my 18. And now I need to think about, okay, how close can I get 4x to a negative 24x? Well, we could multiply, and we should multiply, by negative 6. Because negative 6 times 4x minus 3, well, if I distribute that in, I get negative 24x plus 18, which is exactly what I need it to be. So I'm going to put negative 24x plus 18 underneath. And remember, we are going to subtract. So if I subtract negative 24x minus a negative 24, those are going to cancel. And then we have 18 minus 18, which also cancels, and we are left with nothing left over. So my answer here is going to be a 4x squared plus x, and I can't forget that minus 6 that I had in there. So when I do that division, this is my answer, and it goes in evenly. We have no remainder, which is always nice. So we are done. All right, that kind of also tells us some more information. You might not be there yet in your classes, but because we did our division and we had nothing left over, that tells us that 4x minus 3 is a factor of 16x to the third minus 18x squared minus 27x plus 18. All right, so all of our work here on the side isn't totally necessary, but I wanted you guys to all see where I was getting each of these values from and why I had these values in my answer. And I'm going to write that right next to the top, so we know. Okay, on to our second example here. This one I'm going to do a little bit differently. All right, the only reason I'm doing it differently is because long division here isn't for everybody. If our math and algebra skills are not where we would like them to be, this process could be difficult, or if you do not remember how long division works, it might not be the best method for you. I personally am totally fine with using this next method, which I call the box method. All right, so I am going to divide 3x to the fourth plus 5x to the third minus 13x squared minus 30x minus 8 by x squared minus x minus 3. So it's a little bit more complicated because we are dividing by a bigger polynomial here. This is a quadratic and there are 3 terms to it. So here's how I'm going to do this. We can think of division of polynomials almost like an area model. Let's say we've got this rectangle here and we know that the total area is 36. Well, if I know that one of my side values is 4, I can figure out what the missing side length would be, because what times 4 gives me 36. Hopefully we all know that that answer there is 9. So I'm going to use what we call an area model to help simplify this process a little bit. And it's going to look almost exactly like what I just did in this portion right there. What I'm going to do is I'm going to create a nice big box. And we might not use all of it. I might need to add more, but that's not entirely important. What I'm going to do is I'm going to split this so we have 3 rows. And the reason I want 3 rows is because there are 3 terms in what I'm dividing by. So I'm going to put an x squared, negative x, and negative 3 next to each of those portions. And then I'm just going to split these up into some rectangles here. Just like that example I had with 36 and 4, the inside is going to represent what we're dividing by, right? We did 36 divided by 4 in our heads, which gave us 9. I am going to use the top polynomial, what we are dividing, as the inside area of this entire figure. The outside, such as your length here, is going to be what we are dividing by, and we're going to be looking for the width, if you will, here. We're going to be looking at, hey, this times what is going to give me my answer. And that's another way to think about division. That's how that works, okay? So I'm going to first clean up that 2 on my x squared, and now I'm going to start filling in. What I want to do is I need to slowly but surely start taking care of these values that are part of what we are dividing. So just like we did with long division, I'm going to start with the first value. So in my top left box, I'm going to put a 3x to the fourth. Now, for now, I'm going to ignore all of these other boxes, and we are just going to focus on this one here. Think about the area model idea. I know that the area of this rectangle is 3x to the fourth. I also know one of my side lengths is x squared, so I need to think about what would go up top that when I multiply by x squared, I get 3x to the fourth out. Well, hopefully we realize that that is going to be a 3x squared. What I'm now able to do is I'm now able to fill in the area of these smaller boxes because we have the length and the width of each one. So this first example, this length right here is the same length as this. So that means that to get this area, I multiply 3x squared and a negative x. When I do that, I get a negative 3x to the third. And I'm going to do the same process for that bottom rectangle. This area is going to be negative 3 times a 3x squared, and I'm going to get a negative 9x squared. Now comes the next step, and this one is going to take a little bit of effort to kind of remember. So we got our 3x to the fourth taken care of. As division works, we work our way from left to right to slowly cancel out some of those values. I now need to focus on 5x to the third. Well, if you notice, I already have an x to the third value here. So how this area model works is these diagonals right here, which I will highlight in purple, are going to need to add to that second term. So right now I've got negative 3x to the third, but I want a positive 5x to the third. So what that tells me is I need this top box to be an 8x to the third, because if I add these two diagonals, I get this. And again, the box is supposed to represent the area, so all of these parts in here should combine to give me this polynomial. So right now it does, and now I need to work backwards a little bit. It's kind of like what we did with our 3x to the fourth here. I know the area of this box, and I know that this side length is the same side length as this one. So x squared times what is going to give me an 8x to the third? My answer is 8x to the first power. Now, just like we did before, I can multiply to fill in the areas of my other boxes. I'll get a negative 8x squared here. If I multiply these values, I get a negative 24x. And we're kind of back to our second step in our division, where let's look at our next row of diagonals. So I previously looked at these ones. What I'm now going to do is move down the line and look at these ones. I need these three diagonals to add to my third term here, which is negative 13x squared. Well, I've got a negative 9x squared, and I have a negative 8x squared. Negative 9 and negative 8 gives me a negative 17x squared, which is close, but I am going to need, sorry, that's a negative 17, so I need a positive 4x squared in order for those diagonals to add up to my third term. All right, let's keep the process going. If I know this area and I know its side length, I can find our missing piece here. X squared times what gives me a 4x squared? Well, the answer is 4. And now we fill in 4 times negative x should give us the area of this box, which is negative 4x. 4 and negative 3 should give me this area, which is a negative 12. And we've got another row complete. Now we can look at our next row of diagonals. These diagonals need to add to my next term, which is a negative 30x. Right now I've got negative 24x and a negative 4x, which is a negative 28x. I am 2 x's away. So I need a negative 2x here to complete that diagonal and get it to add to a negative 30x. Well, we might look on top and say, okay, x squared times what gives me a negative 2x? Nothing. We can't work backwards when the exponent here is larger than this one. So we're kind of in a crossroads here, but we can kind of finish this off and think about, okay, well, I have negative 12 here. There's no diagonal to add it to because there's nothing there, but I need it to be negative 8. So what that means is I would need a plus 4 here. But again, x, negative x, times something is never going to give me 4. So we're kind of stuck here, and this is what this tells me, that my answer is going to be what we have so far on the outside, 3x squared plus 8x plus 4, with a remainder of negative 2x plus 4. And that right there is our answer. So box method might seem a little bit more complicated at first, but for a lot of us, seeing the visual aspects and filling in the chart, it gives us a little bit of an easier approach because it's kind of the same idea every time, where this might be a little bit more complicated. However, I learned using long division this way. So it's something I'm comfortable with. You are really welcome to use whichever method you would like. I do personally think the box method is a little bit easier because in the same unit in class, we also do factoring, which you can do using the box method. We do multiplication, which we can use the box method for. So if you are comfortable with it, I would definitely use it. One way we can kind of check our work here is I am dividing something to the fourth power by something to the second, which means I should get something to the second power out, which I do. So it kind of confirms that this works and that we are doing this the right way. Now, whenever you're doing division, if you wanted to, we could take our values here and multiply by these ones, and we should get just about this value up top. And I say just about because, again, we have some leftover values that we didn't take care of because those are part of our remainder. If you looked at this original example, since there was no remainder, if we just multiplied this and this, we would get our original polynomial, which is a great way to check your work if you're not sure if you're doing it right. All right, last example here. I'm going to use the box method again because I think it's a little bit easier for some of us. But this one's a little bit different. I've got 6x to the fourth minus 27x to the third plus 13x squared plus 11x minus 1, all divided by 3x squared minus 1. So how is this one different? Well, if you look at what we're dividing by, it is a quadratic, but it's a quadratic binomial. We only have two terms. Technically in here, there's a 0x to the first power, which we don't really write. When we are doing the division, we need to make sure that we are using placeholders. So I'm going to set up my box. And again, I'm going to split into three terms because I need one for my 3x squared. I am going to use a placeholder row here for 0x and a -1. Now we can complete the process. So I'm going to drop some lines in here to start filling out. And again, I'm starting with my first term in my top left box. So thinking about area, this whole area is 6x to the fourth. 3x squared times what gives me that? My answer here is going to be a 2x to the second. Well, if I know this value, that's this length, then that means I know this length and I know this length. So I can fill in this area by doing 0x times 2x squared, which is a 0x to the third. X squared times -1, it gives me a -2x squared down here. And again, here's the tricky part that we got to remember. These diagonals right here need to add to my next term, which is a -27x to the third. Well, that's a little bit of a bigger number, and we're only at a 0x, so I need -27x to the third to be in there. So same idea as before. This is our area. This is our side length. 3x squared times what is going to give me our -27x to the third. The answer here is a -9x. If I fill this in, -9x times 0x is a 0x squared. -9x and -1 is a positive 9x. And now we are looking at our next set of diagonals, which needs to add to my third term, which was a 13x squared. So I have a -2x squared plus 0x squared. So I'm just at -2x squared. Now I need to get to a positive 13x squared. So this has to be a 15x squared. Well, if the area of this box is 15x squared and it has a side length of 3x squared, then I am going to have a 5 up at the top because 5 times positive 3x squared is 15x squared. So filling going down, 5 and 0x gives me a 0x. 5 and -1 is going to give me a -5. And we are done with another column. So let's look at our next set of diagonals, which is going to be this one. I've got 9x. I need 11x. So this will have to be a 2x. Well, we kind of get to that crossroads where we've got a little bit of an issue. I need this times something else to give me a 2x. And that's not going to happen because the degree here is higher than this one. So what that tells me is we are done and we are now going to be looking at our remainders. Well, I've got -5 and I need a -1. So I'm also missing a +4. So my remainder column is this one right here. My answer is going to be a 2x to the second minus 9x plus 5 with a remainder plus 2x plus 4 all over 3x squared minus 1. So this right here is the answer when I divide 6x to the fourth minus 27x to the third plus 13x squared plus 11x minus 1 by 3x squared minus 1. Again, we kind of talked about this before. I'm dividing something to the fourth power by something to the second. I should get something to the second out, which I do, and that helps. All right, one thing I want to point out is, first of all, these diagonals, they need to all have the same exponent. All right, otherwise they can't add, and then this process wouldn't work out. Another thing that I want to make sure to include is if you notice these exponents, they go from 2 to 1 to 0 to none. That's our remainder. And that works with the last process as well. From 2 to 1 to 0 to our remainder. And it even worked with our long division. 2, 1, 0. So although all of these examples, we ended up with something to the second power, that doesn't have to be the case. We could end up with something to the fourth power, depending on what we're dividing and dividing by. It really doesn't matter. The key thing I want to point out there is our exponents should be decreasing no matter what process we are doing here. Okay, so that is polynomial long division, and I did show you a little bit of the box method. In my opinion, either one works. It does get you the same answer, and as you can see, it might be a little bit easier for some of us. It really depends. It's all about your preference, okay? As always, if you have any questions or comments, please leave them in the comments. Like the video and subscribe, and I will see you all later.